15.3. This I don't think is going to be too bad. I think this will make sense to you guys. We're basically going to talk a little bit more about what exactly does K actually tell us. Okay, so what does it mean if K is really big or really small, or if it's right at 1? Okay, so if K is greater than 1 by a lot, it means the reaction is product favored. Now let's think back to our general expression here for equilibrium. Okay, so we talked about this last time. Concentration of C raised to the C power times the concentration of D raised to the D power over the concentration of A to the A power. Sorry, that's sloppy. Concentration of B to the B power. Okay, and that's for the reaction AA plus BB yields CC plus DD. Okay. Well, since we put the products over the reactants, what that means is if we have, and I'm using different colors here because my daughter's here with me telling me that I should use different colors on this. And she's right. So our products are on the top, right? Our reactants are on the bottom. So if our products are on the top and we end up with a big value for K right here, that tells me that there's more product than there is of the reactants, right? So that's product favored is what that means. So we have a much higher concentration of the products at the end once we get to equilibrium than of the reactants, okay? If our K is smaller than 1, the reaction is reactant favored, okay? So the exact opposite. If it's smaller than 1 by a lot, it means that more of the reactants will be present in equilibrium and less of the products, okay? Again, you got to get this idea straight in your head. Equilibrium does not mean reactants and products are equal to one another. It means that the rate of forward and reverse reactions are happening equally, okay? Or the rates are equal. So it's not about amount, it's about rate when we're talking about the equality in an equilibrium. You just need to remember that. Okay, so the following diagram represents 3 different systems at equilibrium, all in the same size containers. Without doing any calculations, rate 3 systems in order of increasing equilibrium constant Kc. All right, so first one here, we've got red going to blue. Okay, we'll consider red reactant. Now, at the same time, blue is going back to red because this is equilibrium. Okay, but at equilibrium, it looks like we've got 4 of the red dots. It's kind of an ugly green color. 4 of the red dots, and then we've got, I used blue for blue. I should have used red for red. What was I thinking? Ooh, my blue doesn't work very well. Hang on. Maybe now it'll work. Let's see. Yeah, there we go. Okay, had some dust in there. Sorry, I just blew into this thing. That probably didn't sound very good while you were watching the video. All right, so we've got 1, 2, 3, 4, 5, 6 of the blue spheres and only 4 of the red. So what that means is our K here is going to be greater than 1 for the first one, okay? So the second one, ooh, why did they do that? These colors are very hard to distinguish here. So it looks to me like there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of the green and 1 of the yellowish green. So a lot more reactant on that one. So this one's going to be a lot, the K on this one is going to be a lot less than 1. Okay? And then the last one here, 1, 2, 3, 4, 5, 6, 7, 8 red, only 2 blue. So this one is going to be a K of much greater than 1. Okay? So rank them in order. Number 3 is probably going to be our biggest K. I think that's, okay, so they say in order of increasing, so we need to start with 2. And then we would go to 1. And then 3 would be our biggest K value. All right? The volume of the containers is 1 liter, and each sphere represents 0.10 moles. Calculate Kc for each system. Okay. You know, that's a lot of work. But basically what you would have to do for each of these is you'd have to figure out what your concentration is for each of them. Okay, this is a 1 liter container, so basically once you figure out your number of moles, that you've figured out your molarity at that point. but then you have to write your equilibrium expression for each of these. So for example, on the first one, your equilibrium expression would be K equals blue, concentration of blue, over the concentration of red. And it looks like these are all one-to-one stoichiometry in the equation. So, so then you would basically just count how many blues you have, multiply that by 0.1, count how many reds you have, multiply that by 0.1, and solve for K. And they want you to do that for all three of them. So I'm not going to take time to do that on the video. But okay, equilibrium constant for the reaction H2 plus I2 yields 2HI varies with temperature as follows. So we've got our KP. Okay, so they're asking, basically what they're saying here is KP is bigger at a lower temperature. Okay, is the formation of HI favored more at the higher or lower temperature? So if this K is bigger here, 792, then that means at that point we've got more of the HI being formed. Okay, because the equilibrium expression for this one, let's write this in terms of pressure because these are all gases here. So the pressure of the HI squared over the pressure of H2 times the pressure of the I2. Okay. In order for our K to have a more HI favored reaction, we need a bigger KP because HI is on the top of this equation. So the bigger the KP, the more HI is going to be formed. So at lower temperatures, more of the HI will actually form in this reaction. Equilibrium constant. Using this information, write the equilibrium constant expression. Calculate the equilibrium constant. We're going to hold off on that because that's when we get to the next section, when we start calculating equilibrium constants. Okay, now this is part of section 15.3. We need to talk a little bit about this. We got kind of a Hess's law thing going on here. So you remember when you added equations together, you could also add their delta H's together at the end. So you've got an equation here, you've got another equation down here, and you know the delta H's for both. Well, you could add those equations together. You could also add together the delta H's, and you could figure out your overall delta H. Okay, so that's Hess's law. This is similar to that in the sense that some of the things that you did to delta H, you can do similar things to K, the equilibrium constant. But they're a little different, so you have to be able to distinguish these. All right. Do they not have any notes on how that works? Let's see here. Yeah, okay. That's kind of weird that they gave the example problem before they had put these in the notes. So this is one example, okay? Let's say that you flip a reaction, you turn it around in the other direction. Your equilibrium constant is going to end up being the reciprocal of what it was before, okay? So, for example here, on this equilibrium expression right here, okay, you've got the NO2 squared over the N2O4 gives you 0.212. If you want to know what the equilibrium constant is when you flip this thing, you can actually just take 1 over 0.212. That's going to give you 4.72, okay, which is the number here. Now you could just plug your concentrations back in over on this one, but it's easier to just take the reciprocal, okay? So if you know the K for one reaction and you flip the reaction, the equation around, then you need to take the reciprocal of K. All right. Now, again, that's different than delta H, because remember with delta H in the Hess's law, when you flipped an equation, you actually just changed the sign. You didn't change the number. So you've got to know how they're similar and how they're different. All right. We're doing a similar process, but you're changing K in a different way than you were delta H. So second thing that you could do to manipulate an equilibrium constant, let's say that you multiply the reaction by 2, okay? So again, the example here, you've got a coefficient 1 and a coefficient 2. And down here, we've multiplied the whole reaction by 2, so now we've got a coefficient 2 and a coefficient 4. Okay? Now notice what happens when we plug these things in. You find your equilibrium expression to be 0.212 over here. Then you multiply the whole reaction by a factor of 2. Well, you have to square the equilibrium constant. All right? So again, with delta H, you multiply the equation by 2. You multiply the delta H by 2. Here, you multiply the equation by 2. You have to square the K. All right? So just kind of keep that in mind. And then the third thing, equilibrium constant for a net reaction is the product of the equilibrium constant. So when you added up reactions in Hess's law, you just added up the delta H's. Here, for K, you have to multiply the K's together. All right? So an example of this would be these two reactions right here. Okay? So you've got a K value for the reaction in the HF, and then you've got a K value for the reaction in the H2C2O4. When you add those two together, now notice that's what we're doing here, because if you do add them and you cancel out like terms, well, there's a couple of things actually we have to do here. We've got to, there's a lot of things we have to do here. Okay, so we need 2HF, right? In the final equation, the only place there's an HF is right here. So I need to multiply this whole equation by 2. All right, first of all. So that's going to be 2HF, 2H pluses, 2F minuses, and I'm going to have to square my KC over here. All right? The other thing I need to do is the second equation needs to be flipped, because the C2O42 minus is on the reactant side in the final equation, and it's actually on the product side over here. Plus we need those H pluses to cancel out. So basically this second reaction needs to be flipped, and so if I flip it, I'm taking the inverse of the K, right? Then once I add those two together, they should add up to give me this bottom equation down here. Okay, so I'm adding these together, so now I have to add together my K's. So now what I have to do is basically multiply these together. 6.8 times 10 to the negative 4th squared times 1 over 3.8 times 10 to the negative 6. And that's going to give me my overall K, which, are they saying it's 0.12? I'm not sure if that's the answer or not. Let me check. So 6.8 times 10 to the negative 4th squared times 1 divided by 3.8 times 10 to the negative 6. Yep, 0.12. That's what you end up getting for your answer there. Okay, so that's the way that kind of works. So you need to know how to do that. So again, some of you who really liked Hess's law, you're going to like this, but you just have to remember the different rules for K. All right, and that's it for that section. So we'll see you in class tomorrow. I don't think we're going to have another snow day, so I'm pretty sure we will.